Thank you, everyone. Good evening. My name is Martin. I'm the CEO of a company here in Toronto called Repustate, and we do everything text analytics. Today, I'm going to talk to you guys about semantic search and the challenges and some solutions in this growing space. Semantic search is exciting because it touches on all the buzzwords: AI, ML, neural networks, deep learning, all that stuff. So today I'm going to show you kind of some of the interesting problems that we see in this space and how we try to solve them. To begin, what is semantic search? So it's the difference between doing a search like keywords and using Boolean operators to get at what you want. So traditionally you would say something like, if I want to search for text that's about Apple the company, but I don't want apple pie or apple trees or apple juice or apple crumble, I'd have to kind of come up with this complicated query to tell the underlying search engine, no, exclude these terms. Semantic search is kind of doing away with that. And it's more about stating your intent exactly the way you would naturally think and just letting the underlying search engine do its thing because it understands what you're searching. So rather than having these complex queries, you can just say, I want text that has to do with Apple the company. And it just knows that apple pie and Apple computers are two different things. And so that's what semantic search is about empowering users to be able to search text in a more natural way. So there's a few interesting challenges that we stumble upon when we're dealing with semantic search. So consider this problem. Say you have a collection of tweets about coronavirus. How would you find the most frequently mentioned symptoms? So you've got hundreds of millions of tweets over the last 6-7 months, and you want to figure out which symptoms people seem to talk about the most. Or maybe you're trying to predict the next epidemic or pandemic, and you're monitoring social media, and you're trying to keep track of which symptoms people complain about and see if those can act as a predictive metric for when the next outbreak would happen. Say you're in a hospital environment, and these days, fortunately, we don't take notes anymore with pen and paper. Most hospitals have transitioned to digital records, electronic medical records or electronic health records, they're called, EMRs, EHRs. How would you find all patients who have been administered a certain dosage of an opioid topically? How would you do this? How would you scan the clinician's notes? So say they wrote patient given 25 micrograms of a fentanyl patch. How would you find that patient note amongst all the patient notes? Let's say you work in an environment where you need to search text that in a language that you don't speak. So let's say you work in finance, you're a financial analyst, you care about people's opinions or the news in different markets from yours. Let's say you're an oil analyst, news coming from the Middle East would be important. Maybe you work in intelligence and you need to be able to flag certain topics or themes or subject matters. How would you do that if you don't speak the language? Can you even do that? Is that even possible? What if you're in the geolocation space and, in this day and age where people are increasingly concerned about privacy, so they don't want the location on their device to be shared or the location in their browser to be shared? How would you know the phrase, any good restaurants near Ballard or Fremont? How would you know where that is or what that is? How would you resolve that query and return meaningful results to your users? So I know, given the audience, that a lot of you probably are already starting to think of solutions. It's inevitable that technical-minded people, when they're presented with problems, the mind starts to race to some solutions. And maybe the solutions I'll talk about today you're already familiar with. But you would think that some of these are pretty easy, right? Like if there was a document that said LeBron James is looking to win his 4th NBA title, and I queried basketball players, that should come back, right? That seems like that's common sense. And so if you were to use some software from the big billion-dollar companies like Amazon and their Kendra offering, or Microsoft's Azure Cognitive Search, you'd expect a search result, right? If I entered the query basketball players, you'd expect LeBron James is looking to win his 4th NBA title. That document, or if that sentence appeared in a document, you'd expect that search result hit, right? But you'd be wrong. These search engines miss this document completely. And so semantic search in some commercial offerings is still kind of trailing, and it's still definitely a new field and a lot to explore and to improve upon. Before I jump into some technical solutions and how some of the tools at your disposal, I want to tell an anecdote which really states and highlights the difficulty in language. We had a customer, one of our biggest customers. They paid us a lot of money. So when they ask for things, we do exactly what they want. And on a Thursday, I got contacted by a project manager there, and he said to me, "Martin, we need to add support for Polish, and we need it by Wednesday." So in 6 days, they wanted us to add support for a new language we had never seen before, sentiment analysis, named entity recognition, the whole thing. And I thought, okay, well, 6 days, that's pretty much impossible. But I got the team together, and we started to brainstorm, and we started to think, okay, we're going to have to do a sprint over the weekend, and what kind of resources can we pull together? And then I got an email from that same project manager about 2 hours later, and he said, "Martin, forget it. I made a mistake. My manager wasn't asking for Polish. He said, we need more polish. The app was a little rough around the edges, and his manager was asking for more polish." So if even people can mess language up and screw it up, what hope is there for a simple machine? So with that problem stated, let's try to solve it. So there's a couple tools that we can use, and they all work together. By themselves, you can't really solve the problem, but in conjunction with one another, you can start to solve some of these difficult problems that I've stated for you. So we'll talk about named entity recognition, which is identifying people, places, and things in text. We'll talk about word embeddings, something called word2vec, which kind of helps describe which words are similar to which other words based on similar contexts. We'll talk about a knowledge graph and what it is and how it can help. We'll talk about how to search for vectors and how we can do vector comparisons to help solve these problems. And then lastly, we'll touch on clustering algorithms and how those can help in certain contexts. And there's more tools. There's not enough time in 20 minutes to share the whole toolkit, but there's a lot out there, and it really kind of depends on the problem and the industry and the specific domain you're working with. So let's start with NER, named entity recognition. And this is one of the first things that you'll need to tackle when doing semantic search. And that helps you identify people, places, things in text. The name of a location, the name of a medication, the name of a restaurant, the name of a building, whatever it is. So where it's obvious, you want to be able to tag the entity and classify it. So you want to be able to know that LeBron James is a basketball player and that the Los Angeles Lakers are a basketball team. But sometimes if it's not obvious, if it's ambiguous, for example, if it's just the word apple and even further complicated by maybe the A is lowercase, so it's a little bit harder. How do you resolve that ambiguity? So you kind of get a list of candidates. So what are all the possible entities that could fit this word or phrase? And then you start to dig into your tool. So you start to look at word embeddings, you look at the surrounding context, you maybe use your knowledge graph, and you try to disambiguate. And that's how you're able to build up a profile of the entities in a given document. So here's an example of how a knowledge graph can help us out. So a knowledge graph is a large collection of entities and the facts about these entities and how they all connect to one another. So for example, if there was a knowledge graph that had Apple, the company, you would have a link. So if you're trying to visualize a graph, you would have a link from Apple to Tim Cook, and from Apple to Cupertino, California, and from Apple to iPhone. So all the entities and how they're related, that kind of all gets graphed. And then for each entity, you can have metadata or facts about the entity. And so when you have this massive knowledge graph, you can really start to infer meaning and context. So if we took the sentence, Bruno Fernandes scored a goal in United's 2-0 win, Bruno Fernandes is pretty unambiguous. There's only one guy named Bruno Fernandes who scores goals. But United is kind of ambiguous. It could be United Airlines, I suppose. It could be United Way. It could be Leeds United. It could be Newcastle United. There's a lot of football teams who have United in their name. It's a very common suffix. So how would we know which United it is? So if we were to consult our knowledge graph, we would know that Bruno Fernandes is an entity. One of his facts or metadata about him is that he plays for a team called Manchester United. And then we could follow that connection along our knowledge graph, and we would get to the Manchester United node, and we would see that United is an alias for Manchester United. And then we could, with a relatively high degree of probability, say, yeah, that's the right United. So in this case, United should resolve to Manchester United. You see a knowledge graph all the time when you do Google search results, those little info boxes on the right that are often taken from Wikipedia. Those are knowledge graphs. And so when you have a knowledge graph and when you kind of are able to persist it and codify it properly, you're able to start to expose interesting search possibilities. So if you had all this data about a basketball player or about athletes and you knew they played basketball, and you could support a query like find me all basketball players, or find athletes earning more than 30 million a year, or find athletes from Ohio who are older than 30 years old. So just from relatively simple data, once it's all connected, when all the nodes are all connected to one another, you get a really powerful apparatus on which you can build very complex queries. So if we put it all together, we can start to represent text documents as vectors and not just by the literal words that they're contained. And in addition to the entities, you can store and represent a document by the metadata. And a common practice in machine learning and AI is to convert text to numbers. Sometimes you use hashing algorithms like murmur3 hash or something like that, just to get a unique number for each word. You can kind of apply a similar approach in semantic search if you want to represent one document as a unique representation of entities and their respective metadata. And why you want to do this is because now you can start to do comparisons. There's a lot of well-known approaches to doing document similarity, like the cosine distance, cosine similarity. You can compute the Jacobian distance between vectors. But once you have your documents represented like this, it really opens up the possibilities to not only do search by entities, but now you can do cross-lingual search. So if we take a document that's in English and we take a document that is in Arabic and we resolve the entities within each, as long as each entity has a canonical ID, now we can start searching across multilingual corpus. And so now you can start submitting English queries to an Arabic corpus or an Arabic query to a Russian corpus, because under the hood, everything is being converted into vectors with numerical elements. So you've almost kind of done this translation without really doing a translation. You're still representing the underlying data as a collection of entities and their respective metadata. But again, it really removes the barriers to translations and languages when you agree on a more standardized internal representation. Geoclustering is another example, and this kind of comes back to that challenge, that interesting challenge I mentioned in the beginning. So if we had a query, anyone know good restaurants near Ballard or Fremont? How would we solve that? How would we even begin? So one possible approach is you find all the locations called Ballard, find all the Fremonts, define a maximum distance through a distance function between the two locations, and you use that distance to be considered close enough. So if two locations are 500 kilometers apart, that's not close enough. Nobody in their right mind would be asking for a restaurant recommendation for two locations that are 500 kilometers apart. So you have to apply some sort of heuristic, some sort of common sense to the problem. It's not entirely unbounded. So once you have a maximum distance and a distance function, now you can start to find the clusters where 2 points are close to one another. And then of all those clusters, find the one where they're the closest. And then that's probably, again, we rely on probabilities and some common sense. And we could say, yeah, that's probably the two locations that a person was referring to. So this algorithm I'm describing, it's not something that I invented. It's something that exists. It's called dbscan. And dbscan is great because unlike other clustering algorithms, more popular ones, like for example, k-means or k-nearest neighbor, you don't need to know how many clusters there are ahead of time. You can just tell the algorithm, look, here are all my points. Here's my distance function. Here are the minimum number of points I need for a cluster to be considered valid. Go. And this algorithm will find all the clusters that appear. So this Google map image you see, these are all the Ballards and Fremonts that we were considering. And then the algorithm, dbscan, will go and find all the clusters that fit our criteria. And then we'll sort them at the end. And we'll try to find which one best fit our criteria and which of those two Ballard and Fremonts were closest to one another. And that's how we would know where to look for restaurants. The answer, by the way, is in Seattle. There's two neighborhoods in Seattle that are, I think, about 500 meters or one kilometer apart. And that's the Ballard and Fremont that this approach would return. So to summarize, semantic search, it's a challenging field. There's a lot of ways to solve problems. There's a lot of tools at our disposal. The solutions and the approach you adopt is often industry specific and often can require specific tooling and training on the data. Once you start to consider things in a multilingual context, it makes things much harder, of course. As always, most of the research that's out there generally focuses on English. Most of the training data or tag data focuses on English. But you can kind of be clever and you can try to adopt techniques that remove that barrier, like I mentioned about standardizing on a vector representation. And that's how you can kind of tackle some of these multilingual issues. So I hope that was a good primer and I didn't go too technical. And I hope some of you now have a renewed interest or initial new interest in the world of semantic search.